Hello, my name is Mark McComb, Technical Training Engineer in the Security, Microcontroller, and Technology Division here at Microchip. Thank you for viewing this web seminar detailing a few design guidelines for Microchip's capacitive mTouch sensing solutions. The discussion presented here assumes that you have viewed the previous web seminar, Introduction to mTouch Capacitive Touch Sensing. The main points from that web seminar will be briefly reviewed for clarity, including the functional characteristics of a capacitive mTouch sensing solution, along with basic touch sensor construction. The primary focus here is to provide some basic design guidelines as they relate to touch sensor pad size, placement, cover plate material selection, and mounting recommendations. First, let's take a moment to review the basic components of Microchip's capacitive mTouch sensing solution. As discussed in the Introduction to mTouch Capacitive Touch Sensing web seminar, a copper sensor pad is created on a printed circuit board that will produce a capacitance in conjunction with grounds located elsewhere in the design. A covering plate is secured over the pad to create a touch surface. Touching the covering plate over a pad creates an additional parallel capacitance essentially coupled to ground. This adds to the overall capacitance generated by the touch sensor, which will be used to detect a finger press. The capacitance generated by the touch sensor is used in conjunction with a dual comparator with SR latch peripheral found on newer PIC MCUs, along with external components to generate a relaxation oscillator. The operation of this oscillator is discussed in great detail in the Introduction to mTouch Capacitive Touch Sensing web seminar and should be referenced for more information. Suffice to say that this configuration will generate an oscillation on the Q-bar output of the SR latch. The frequency of oscillation will be determined by the capacitance generated by the mTouch sensor represented here by C sub S. Alone, the touch sensor generates a particular frequency of oscillation. The frequency of the oscillator is then measured in a fixed interval using both timer 0 and timer 1 peripherals. Any shift due to a user's touch is detected and validated in software. However, this isn't the end of the story. Some design guidelines will need to be considered when developing any capacitive mTouch sensing application. The basic capacitance equation we have looked at in previous web seminars will be used as a reference for most of the design guidelines introduced here. Looking closely at the variables that make up this equation, you may notice that each could be easily altered depending on the implementation of this technology in your design. For example, the size of our touch sensor pad will have a huge impact on the capacitance generated by the sensor. The greater the area, the greater the capacitance. Therefore, increasing the area proportionally increases the capacitance, allowing better detection and sensitivity. Notice that this equation does not take into consideration the shape of the pad. This means that some latitude can be taken when going for a more aesthetically appealing pad design. So how big should your pad be? As a very general rule of thumb, the area of the pad should be about the size of the average fingertip, approximately ½ inch by ½ inch. Typically, we will be implementing more than one touch button in an application. Therefore, another factor to consider is the proximity of adjacent touchpad sensors to each other. Here an exaggerated side view of two touch sensor pads are shown, along with the printed circuit board and covering plate. Once a finger press is introduced, a capacitance large enough to trigger a false press on a nearby sensor could be generated if positioned too close to the target sensor. In this situation, two of the variables from the capacitance equation are considered: area in the numerator and distance in the denominator, as they both relate to the finger press. Moving the nearby sensor away from the target sensor will increase the distance value in the capacitance equation in relation to the finger press. Also note that the area variable will also decrease due to simple geometry, contributing to a further decrease in capacitance. Therefore, to minimize the sensitivity of nearby sensors to a finger press, adjacent sensors should be placed appropriately. Maintaining a distance of around 1/4 of an inch between adjacent sensors should provide sufficient insulation from the finger. An alternate method of decreasing nearby sensor sensitivity is the introduction of a ground trace between adjacent sensors. With the ground trace so close to each touch sensor pad, a larger base capacitance is generated. The capacitance generated with the introduction of a finger press will therefore have less of an effect on the percent shift of the oscillator frequency. This attenuation can be manipulated by altering the area of the ground trace. The greater the area of the ground trace, the greater the attenuation. Yet another solution is to create a relief in the covering material between adjacent sensors, introducing air into the space. Since air has a very low dielectric constant, or E sub r, closer to 1, a very small capacitance is created within the gap in series with the capacitance on the nearby sensor. The total of both capacitances therefore approaches the smaller air gap capacitance, minimizing the chance of a false trigger on the nearby sensor. Once the sensor pad design has been optimized, we now need to consider the traces that connect them to the PIC microcontroller. Shown in this slide is a touch sensor pad on the top side of the printed circuit board. Directly beneath the pad is a via connecting to a copper trace. There is a chance that a system could be sensitive enough that a finger press directly above a trace could trigger a button press detection on the associated sensor. There are a couple of solutions for this. The first is dealt with in software by experimenting with sensor thresholds in the button press detection algorithm. However, some caution must be used when using this method, as setting thresholds too aggressively could reduce reliability for different users. Note that each user will produce a different capacitive shift. The second method introduces a ground pad placed directly opposite the trace. This solution works, but remember, a decrease in the distance between ground and sensor will increase the sensor's base capacitance. Therefore, it is suggested that traces be routed away from areas that have the potential of coming into contact with finger presses. Another consideration with trace placement is in relation to other sensors on the board. In this slide, two adjacent touchpad sensors are positioned so that the trace from sensor 1 passes directly below sensor 2. This configuration can produce the condition shown wherein a parasitic capacitance is generated between both sensor pads. A good rule of thumb when laying out your design is to ensure that areas underneath touch sensor pads are kept clear of traces altogether. Some other things to consider as they pertain to circuit traces. Whenever possible, traces should be kept as small as possible and positioned away from ground sources and other traces. This will minimize the occurrence of unwanted parasitic capacitance or inadvertently coupling sensors together. We have covered some basic design guidelines for touchpad sensors. Let's now look at the covering plate that will provide the touch surface in our application. Sensor sensitivity will vary with thickness and composition of the material used. In capacitive sensing applications, it has been found that extremely thin plate thicknesses make for a more accurate and sensitive sensor. Referring back to the capacitance equation, we can clearly see one reason why. As the denominator representing the distance between our two plates increases, the capacitance will become smaller. The capacitive mTouch sensing system has been tested and found to work well with window glass and plexiglass thicknesses of 2 mm to 5 mm. Other materials could be used. However, attention must be paid to the dielectric constant of the material. As we saw earlier in this web seminar, covering plate thicknesses will also directly impact the area variable in our capacitance equation. For example, as the covering plate thickness increases, notice that the difference in area of the nearby sensor actually approaches that of the target sensor in relation to the finger. Therefore, for optimal designs, the thinner the covering plate material, the better. An important consideration when choosing a material for a covering plate is its permittivity, or dielectric constant. This constant defines the amount of electrostatic energy, or electric field, that can be stored by a material when a given voltage is applied to it. As we can see in the capacitance equation, a higher dielectric constant produces a greater capacitance. Some dielectric constants for commonly used covering plate materials are plexiglass defined at approximately 2.25 to 3.5 and glass between 4 to 8, depending on the type of glass used. As you could probably guess, considering the dielectric constant shown here, glass can maintain higher capacitances with greater thicknesses than could covering plates made of plexiglass. Dielectric constants for materials are readily available. Let's take a moment and look at some other considerations for a capacitive mTouch sensing design. What about water on the touch surface of our application? Water has an extremely high permittivity of 70 to 75 in liquid form and around 2 to 3 if frozen. Therefore, water drops on a touch surface has a potential of being sensed as a sensor button press. Water covering a number of buttons could trigger multiple presses. Furthermore, touching a water puddle spanning multiple sensors could set them all off. Microchip suggests a percentage-based voting routine described in the application note AN1103, Software Handling for Capacitive Sensing, referenced at the end of this web seminar. By averaging in the relaxation oscillator frequency to the steady-state environment, false triggers can be minimized. Ultimately, the best solution is tilting the complete system in environments prone to water to allow drainage off of the touch surface. Certain covering materials may also be used that cause water to bead. However, dielectric constants for any additional materials must be carefully considered. Similarly, ketchup and mustard could cause false triggers due to their high moisture content. Especially in a splatter-type environment, a downward shift similar to a finger press can occur. The same averaging techniques described for overcoming false triggers due to water can also be used here. Alternately, you may consider using a press and release detection scheme. Here, a specific window of time is used in which a press and release must occur. Anything too fast or too slow is not considered a press. One solution incorporates an algorithm in which an LED lights with the user's touch, but an action is not registered in software until the user releases the press. Another design practice to consider would be to mount devices such as the PIC MCU on the opposite side of the printed circuit board to the sensors to create a flash or flush surface to accommodate covering plate and minimizing air gaps. Again, avoid placing parts directly beneath the sensors. Centrally locating components may make routing traces easier and minimize disrupting sensor traces. Let's take a moment and discuss how we would package all of these components together into our final application. There are many ways to put together a completed system. This is simply one of them. You may choose an alternate method. This construction sandwich begins with the printed circuit board and sensors. Next, a layer of paper is placed over the pads with graphics to indicate button locations. This is an inexpensive method that gives the designer freedom to produce an end product that aesthetically complements its environment. Alternately, you may consider silk screening the bottom side of the cover plate. The construction sandwich is then secured using an adhesive such as glue or double-sided tape to give a clean look to the design. Using an adhesive of some sort will minimize air spaces between each layer, which will optimize the capacitance of the system. Let's summarize what we have covered in this web seminar. During the course of this web seminar, we have looked at a number of design guidelines to optimize your capacitive mTouch sensing application. Careful consideration must be taken, especially during the layout stage of the printed circuit. Sensor size, placement, and connectivity to other components will ultimately make or break the application. Covering plate materials and thicknesses must be chosen to optimize sensitivity of the system to a user's touch, while minimizing interference with other sensors. Some suggestions were offered in the final packaging of the design. The designer may find that other packaging methods better suit their application. For more information on Microchip's capacitive mTouch sensing solution, please refer to the application notes listed here. Future web seminar topics will include software algorithms, multi-button configurations, and an overview of the mTouch software development kit. You may also be interested in visiting the mTouch Design Center at www.microchip.com/mtouch. Here you will find links to the most current information and resources for this technology. My name is Mark McComb, and I thank you for viewing this web seminar.